My name is Ryan. I'm a postdoctoral researcher here at McGill, and this morning's session is on a topic that is near and dear to my heart, polarization. And to kick us off is Jiarui, who will be giving the overview talk on polarization.
Yeah, thank you very much. Good morning, everyone. I'm Jiarui from NAOC, and I'm postdoc in Weiyang's group. Today, my topic is about probing the origins of FRB through polarization observations. This slide shows the earliest FRB polarization observation. The sentence I like most in this paper is that new instrumentation can decrease the time between observation and discovery from years to seconds. And PACS discovered this source in 2040, and they trigger follow-up observation. They first got the polarization observation result as shown in the figure, and they gave the limit of redshift less than 0.5. They didn't find any counterpart of the multi-wavelength observation. So 10 years later, what new insight do we have about FRB and what polarization observation can tell us? The most important problem is the possible origins of FRB. The milestone observation is that we found magnetite is one of the possible origins. This evidence is given by SGR 1935 and FRB 2004-28. The SGR 1935 is known for emitting short bursts of gamma ray and X-ray, and FRB 2004-28 is the first FRB detected within the Milky Way and definitely linked to the SGR 1935. This left figure shows the timelines of the high energy and radio observation. And the middle two figures shows the radio burst detected by CHIME and FAST. After the FRB, several months later, the SGR 1935 enter a pulsar phase as shown in the right figure. It shows the timing result of the in the pulsar phase. So the coincident radio and X-ray bursts strongly support that magneta are a source of FRB. And for active repeaters, regular repeaters and non-repeaters, they may not have one single origins. In Bin Zhang's review paper, he lists the possible origins of FRB. The light blue box shows the observational fact, and we can find the magneta channel is currently the only known paceway that can produce FRB. So how polarization can help us understand FRBs? The way the radio wave polarize can tell us where they come from, what surrounds them, and how they travel to us. So my talk will divide it into three topics, that is the radiation mechanism, the environment property, and the propagation effect. First is the radiation mechanism. There are two types of model, that is the pulsar-like model and the GRB-like model. For the pulsar-like model, the radiation is originated within the magnetosphere, and for the GRB-like model, it is related to the relativistic shock outside the magnetosphere. One thing these two models debate is that whether FRB can propagate from the magnetosphere. In Brodow's paper, he finds the cross-section of the electron scatter wave is very large when K perpendicular to B. But that is extreme saturation. Actually, FRB wave can propagate freely in the open field line. Details can be found in Yuan Hong's paper. In the left, I list some basic definition of polarization. And in CHIME's recent statistic result, they find there is no significant difference of repeater and non-repeater in terms of the linear polarization degree and RM. And in the early observation, the detected bursts always have high linear polarization and flat PA. But with the accumulation of data, we find some bursts with high circular polarization degree. As shown in this slide, these two figures both from one source, that is FRB 2020-11-24A. And the left figure result is from the PACS observation, and the right is from FAST observation. As shown in the right figure in Jin Chen's paper, he found very high circular polarization degree can reach unexpected 19%. So one key question is whether the circular polarization is intrinsic to the source or induced during the propagation. Actually, in FRB, circular polarization is relatively rare. As shown in this left figure, it shows the correlation of the linear polarization and the circular polarization degree. This green sector contains the burst of 68% of all the bursts. You can find most of the bursts have high linear polarization. The same is as in the entire astronomical phenomena. In the right figure, the x-axis shows the brightness temperature and the y-axis shows the circular polarization degree. The FRB are in the right region, both with the high brightness temperature and high circular polarization degree. And only solar bursts and Jupiter can reach such high circular polarization degree in the astronomical phenomena. And here I list some observation facts related to circular polarization. As shown in Jin Chen's paper, we found rapid polarization change as shown in this figure, both in PA and the circular polarization degree in the time scale of 30 milliseconds. So the out of magnetosphere propagation effect will both affect the linear and circular polarization. So for the extra plasma, it is difficult to cause such rapid change in polarization. And in the middle figure, we find no strong correlation between flux and circular polarization. For the off-beam Weiyang geometry, it can produce circular polarization, but this burst will have lower flux than other bursts. We didn't see that in observation. And in this right figure, we found circular polarization of some bursts is independent of the frequency. So this can't be explained by the Faraday conversion because Faraday conversion is frequency dependent. So the intrinsic radiation mechanism and the propagation effect both fail for the GRB-like model. As shown in Yuan Hong's paper, he discussed the radiation mechanism and the propagation effect both inside and outside the magnetosphere, including the curvature radiation, inverse Compton scatter, cyclotron absorption, and the Faraday conversion. The conclusion is that high circular polarization favors magnetospheric emission model. And the next observation related to radiation mechanism is PA swing and RVM. This is a well-known rotation vector model, and this formula can be derived from the spherical geometry. And the alpha is the inclination angle, beta is the impact parameters. In Luorei's paper in 2020, they found some bursts have such PA swing, and in recent CHIME results, they found FRB in a nearby host galaxy, and it shows 130-degree PA rotation in about 2.5 milliseconds. This PA swing and the S-shaped PA both support the magnetospheric origins. Consider the possible origins of neutron star. They can also rule out the very short period pulsar in CHIME's source. And in repeating bursts, in Xiaohui Liu's recent paper, he found the PA variation are very fully consistent with RVM of total of 46 bursts in total 1,700 bursts from three active repeating FRB. This figure shows the RVM fit result and the observed PA. However, we found that these inferred parameters is inconsistent with each other, as shown in this left figure. The different color shows the different repeaters, and the violin plot represents the distribution of the parameter of period alpha and beta. So the most of the bursts have constant PA. It perhaps indicates that the central agent is an Allied rotator, or it has a very long spin period. But some of the bursts show significant PA variation and can be well fitted by RVM. And this tells us the magnetic configuration is dynamically evolving. This is my work about the sudden polarization angle jump. We found 3 bursts with PA jump in the time scale of millisecond in thousands of the bursts in FRB 2020-11, 24A. The energy of these 3 bursts is higher than most any other burst. It perhaps indicates the same mechanism of pulsar and FRB, despite they have huge energy difference. And for the burst 1, these bursts have a more complex methodology. As shown in this figure, we plot IQUV as a function of time and frequency. You can find it. This burst is consisting of the different components. If we cut frequency, as shown in this left panel, we will have flat PA with the PA jump shown in the lower frequency. But the total profile has a PA swing. This PA swing is composed of the superposition of different components. And another interesting thing is that we found in the lower frequency, this left peak and the right peak, it has a totally different RM. As shown in the right figure, if we derotate using the average RM shown in this black line, we will get the jump of the 66-degree jump shown in this black dot. And if we derotate using their own RM, shown as this in this red line, we will get a 19-degree polarization angle jump shown in the red dot. So RM can change very large in such short time scale in millisecond. And in Yuan Hong's paper, he discussed PA jump in detail, and the intrinsic mechanism is favored. The bifurcance and plasma lensing is disfavored. So the PA jump in these 3 bursts can be explained by the incoherent superposition of the 2 orthogonal modes. The millisecond time scale observed in the PA jump imposes a strong constraint on the emission region in a magnetar's magnetosphere. So for radiation mechanism, our conclusion is that at least for some FRB, the mechanism is pulsar-like, and the radiation is inside the magnetosphere, and the magnetic configuration is dynamically evolving. And my next topic is the environment properties. Here is the background of the Faraday rotation and the Faraday conversion. If we assume that the income wave is 100% linear polarized, in the case of the B field is parallel to the line of sight, the plasma mode will divide it into 2 circular modes. One is left and another is right. And these 2 modes have different group velocity and phase. So for the outcoming wave, it will be linear polarized. That is, and the PA slightly rotates. That is a Faraday rotation. If we plot the Stokes parameters on the Poincare sphere, the trajectory will be a circle around the v-axis. And in the situation of B field is perpendicular to the line of sight, the plasma mode will divide it into 2 linear mode, and one can image that the 2 orthogonal linear mode will generate the circular mode. That is a Faraday conversion. If we plot the Stokes parameter on the Poincare sphere, it will also a circle, but not around the v-axis. So RM quantifies how much plane of the linear polarization rotates, and the extreme RM indicates the presence of a highly magnetized dense plasma along the line of sight. As shown in this left figure, the highest RM observed in FRB is FRB 121102. It can reach the 10 to the power of 5. Is larger than the magnetite and the galactic center pulsar. Fast observed this source for a long time, as shown in this red figure. We found that both RM and DM have decreased with time. This trend can be explained by the early phase supernova explosion, and the more observation perhaps strengthen the orange of the young magnetas. except for FRB 121102, multiple FRBs shows temporal variation in days. Combined with the data from the other paper, Cherry-NG summarized the RM variation of the repeaters. The special one is the FRB 800916. It has a 16-day activity cycle as the RM variation shown in this figure. The RM evolution of this source lack periodicity correlation with the activity cycle. And in fast new result in Li's recent paper, we found RM flare. This RM change very large in time scale of days. And this RM flare suggests a dense magnetized clump moving across the line of sight. And this possibly caused by the coronal mass ejection, and it can be explained by the companion star that provide this stellar flare. Except the RM flare, in the earlier observation, they found RM period in 200 days, as shown in Yifang Liang's paper. And this period is consistent with the RM flare predict. And also in Zhang Weixu's paper recently, he found RM period of 26 days in FRB 2020-11-24A. And he got this period using Lambscago and wavelet. You can find this period is mainly dominated by the first and third episode of this source, shown in the black and green region. Perhaps we need more active data to confirm this period, but this source turned off for a long time. In addition to the long time scale RM variation, RM also shows variation in milliseconds, both in repeating and non-repeating bursts. In fast results, we found in this consecutive burst with interval of 15 milliseconds, the RM change can reach 50. And as shown in Sherman's paper, they found the RM of non-repeating burst of the subcomponent can variation with time, showing these scatters. RM also saw side change. In Cherry-NG's paper, she found two sources show side change of RM among the 26 repeating FRBs. And together with the previous published one, the FRB 190520B, its RM twice changed its size. So RM side change indicated reversal in the direction of the magnetic field lines, perhaps can be explained by the binary model. So for the environment property, periodic and side change behavior in RM would support the binary model. The next is the propagation effect. In Xu Hong's paper, we found the evidence of the Faraday conversion. It shows oscillation in the linear polarization degree, circular polarization degree, and PA. And if we consider the linear to circular polarization conversion, one can extend the Faraday rotation to the generalized Faraday rotation, that is the GFR, using the parameter of spectral scaling index alpha. And Pawan using this method to test the observation of 180301A. And he got a good fit of the Stokes V and Q, but the V and U, but the Q have a relatively large residues. This also using the magnetized work. So for the homogeneous magnetized plasma medium, Weiyang gets an analytical solution of the transformation equation. Compared with the GFR model, they offer a more physical description of FRB magnetic environment. Details can be found in his talk and Tian-Cong's talk. And another propagation effect is frequency-dependent depolarization. In Feng Yi's work, he observed 5 active repeaters in a very large frequency range, and he found the frequency-dependent depolarization as shown in this figure. This can be well modeled by the parameter sigma Rm. The depolarization Rm scatter can be read as that. This red figure shows the degree of linear polarization and Rm. For the repeater and non-repeater, they seem different, perhaps indicates they are in the different environment, but it still need more data to test. In DSA's results, they found 25 new FRB. 3 of them have total polarization consistent with 0. So according to their frequency and polarization degree, they found no significant RM in these 3 FRB. This favor multipace RM scattering in this source. The next propagation effect is the plasma bifurcance. In SCAP result, they found 2 bright polarized bursts with intra-burst RM variation showing the purple scatter. And they also found time-dependent circular to linear to circular polarization conversion. This can be well modeled by the grid circle on the Poincare sphere, and it's evidence of the plasma bifurcance. This is my summary slide for the propagation effect. We can get a physical description of FRB magnetic environment. And in my talk, the cited paper in blue are both from the FAST FRB K-Sense project. And we are open for collaboration. Thank you.
Okay, we have a few minutes at least for questions. Any questions from anyone? Adam?
Hi, thank you. I don't, I'm not an expert in polarizations. This might be a very naive question, but you detected PA swing in a repeater. If it's to do with the rotation of the object, like a pulsar, wouldn't you detect the swing every burst? No, not just in like 3 out of 1,000 sort of thing.
You said in FRB, right?
Yeah.
We only detect 3 bursts in total of thousands of bursts have PA jump.
From a repeater?
Yeah, from repeater. Right. This is a very active repeater.
Yeah, so I guess my question is, if it was a pulsar, wouldn't you expect the PA swing to happen every single burst? Or
no. In pulsar, actually, I have this slide, but I have no time to show you. In pulsar, if the total profile has PA jump, some of the single pulse have the PA jump in this PA. Yeah, only some of the bursts, not all of the single pulse. Yeah.
Thank you. Ryan, I wanted to.
Please speak louder.
Hi, I'm Kavya Shaji from University of Sydney. Thank you for the nice talk. So there are sources which exhibits like high DM, but they are like shown to have very low RM, like nearly 0. What could be the mechanisms or responsible for this?
Actually, it depends. I think. In another very highly active burst, it has a RM near 0, but we also shows many polarization results in this source. Actually, I think perhaps it is in a clean environment, so we can answer your question after find new FRBs, more observations.
Thank you.
Thank you.
Okay. Are there any questions online? Okay. Oh, here, Mouse.
Yeah, thank you for the talk. I had a question, I guess, in terms of how do we distinguish the most unique cases, like ones with we have a couple of FRBs that have PA swings or significant RM variation? How do we, and they could suggest a magnetospheric origin or different things about the progenitor. How do we distinguish those from whatever the most common cases for FRBs are?
Most of the bursts, the RM variation shows no regular, but some of them shows periodicity. I think the periodicity is the evidence for the binary model for the we can confirm that, I think, because the periodicity is not very convincing to answer that. I'm not sure. Compared with the observation of pulsar, in binary pulsar, the RM often not show the periodicity. So perhaps we need more observations, I think. Yeah.
Thank you.
All right, let's thank the speaker again.
Okay, our next speaker is Mason Ng, colleague of mine, who will be presenting on baseband catalog to polarization results.
Cool, thanks, Ryan. So I'm usually tech support, but I'm Mason. I'm actually a postdoc here at McGill. I'm an extra astronomer by training, but I'm here today to talk about the first look at the polarimetric properties of FRBs from the CHIME FRB baseband catalog 2 or BaseCat 2. So to orient ourselves, Jiarui has already given a nice introduction, but just to orient ourselves, a reminder that polarization is just the orientation of the electric field in the propagation of an electromagnetic wave. And as Jiarui also was motivated in the previous talk, we care about polarization because we get insights into the emission mechanisms and also the local magnetoionic environments in and around FRBs. And also a high linear polarization, for example, gives us strong, highly ordered magnetic fields. And in terms of how we do this, we can construct Stokes IQ-UV parameters from the XY linear feeds, and we can systematically study the polarimetric properties through large data sets that I'll describe in a short while. But I do want to lay out some relevant definitions for now, and so that we're all on the same page. So we have the linear polarization fraction, which basically tells us how aligned the electric field vectors are. So imagine all of you in the audience, you're all waving Canadian flags because you're in Canada. And the linear polarization fraction tells us whether you're all waving the flags in the same direction or in sync chaotically. But I won't be talking about the polarization angle today, but it basically refers to the orientation of the electric field vector itself. And then there's the Faraday rotation, which is just telling us how much the electric field vector rotates as it passes through a magnetized medium. And it's basically related to the electron density and also the magnetic component, a magnetic field component along the line of sight. And this can be negative because the magnetic field has a direction. And likewise to what you hear from like the DM budget, there's also an RM budget with various distributions. There is can't read my own slides, ionospheric and the IgM contributions, which is roughly 0. And then there's also the Milky Way contribution, which we can use a galactic rotation, Faraday rotation sky map to do so. Although there are some uncertainties there, and in terms of how those uncertainties can affect FRB measurements, take a look at Ayush's latest paper on the archive. But basically what you have left over is the host RM that's scaled by 1 plus Z all squared, or what I'll call the extra galactic RM from now on. So before talking about BaseCat 2, I want to quickly summarize results from the first baseband catalog, or BaseCat 1, with polarization measurements from 128 non-repeating FRBs over 400 to 800 megahertz in the CHIME band. And out of that 128, about 89 have significant detections, significant meaning above 6 sigma. And among some of the key results are that there's no seen dichotomy in the distributions of observed linear polarization fraction or the extragalactic RM. And there's also between the non-repeating and repeating FRBs. So just to put some of the words I just said into diagrams, I'm showing the top here the distribution of the, let me move this up. the distribution of the linear polarization fraction between unpolarized and polarized FRBs in gray and in blue. And then on the right is the cumulative distribution function for the comparison between non-repeating FRBs in blue and repeating FRBs in orange. And then below is a similar type of diagram, but this is for the absolute value of the extragalactic RM, histogram on the left, and cumulative distribution function on the right. And simple p-values from simple Kolmogorov-Smirnov or Anderson-Darling test suggest that the two groups are drawn from the same population. So here's a visualization of the Basecamp 1 sample with the 89 polarized FRBs in white and 29 unpolarized and 10 that are limited by the instrumental polarization. And now so far, oh, did it load? Maybe not. Oops. I wanted to run animation. Okay, well, for Basecamp 2, we have quite the expanded sample. So the processing of the baseband data has been led by several folks that's up there, including myself. And the caveat is that we're still processing the events and verifying more of them. And we still need to inspect the polarization fits in depth to determine the events that are limited by the instrumental polarization, but it's coming along. And to put some numbers to what I just said, the detection threshold for polarized unpolarized is the same as in the Basecamp 1 sample, which is 6 sigma. And for any upper limits on the linear polarization, it's 6 over the intensity signal to noise. But the sample so far, here I've listed, there are 997 polarized non-repeating FRBs and 182 unpolarized. And the preliminary visual comparison that with repeating sources will make is facilitated with the published catalog by Jiarui et al., no relation. And in all cases here, we've calculated the structure maximizing DM. And I should also note that a very simple sanity check we did was, we did a simple KS80 test, implying that the underlying distribution sample for Basecamp 1 and 2 were roughly the same. So onto the distributions itself for some of the relevant quantities. I'm showing both histograms on the left and right. On the left are the comparison for the linear polarization fraction, and on the right is for the extragalactic rotation measure. And the caveat is that for values of RM below about 10, there's, we're still investigating and likely limited by instrumental polarization there. So I guess be careful. Although some preliminary statistical tests suggest that we don't see any significant differences between the non-repeating and repeating populations in either of the two quantities or metrics there. But if I now just focus on the non-repeating sample itself, and let's think about the expectations for the extragalactic RM as a function of the extragalactic DM. And if you assume that the DM and RM components, the contributions come from independent sources along the line of sight, you might perhaps get something like this, maybe, because of the 1/1 plus Z factor difference between the RM and DM. But in reality, you get something like this. And focusing on the non-repeating sources in blue, with the caveat, again, that the low RM environments events may have polarization leakage are not accounted for properly yet. And but if you do a simple Spearman rank correlation test between between the extragalactic RM and DM for the non-repeating sample, you get a p-value of something like below 0.006. And the reason why I quote that value is because in that same exercise that was being done in the previous sample with the 128 non-repeating FRBs, in Basecamp 1, that was the value that we got. So I will, at the risk of abusing p-values too much, I will just say that we might see something, but we still need to do more to ascertain the relation. But going back to the physical picture, if the extragalactic DM, which has both the IGM and the host galaxy contributions, if that is a proxy for distance, take my word for it for now, then we would expect the extragalactic RM to be lower at higher DMs just because of the 1 plus Z squared denominator for the RM. And so maybe the high RM values we see here may indicate significant magneto-ionic environments. But just to explore and look at that extragalactic RM a bit more, here is this probability density function of the extragalactic RM without taking the absolute values. And you can see from the Basecamp 1 sample that's in blue and the Basecamp 2 sample that's in orange, the distributions look roughly similar, about 0, which is kind of what we expect. But our first thoughts, or at least my first thought, is that if you have a conglomeration of random distinct regions contributing to the RM budget along the line of sight, the central limit theorem would indicate or dictate a Gaussian distribution for the extragalactic RM here. But if we were to try to fit a Gaussian, so for in this case, pink for base cat 1 and purple for base cat 2, and some of you could already probably tell, you don't get a very good fit. In particular, the wings of the distribution aren't very well modeled. But if we try something like a Lorentzian, you get a slightly better fit, at least for the distribution around plus minus like 1,000 or so in the wings. But I mean, it's not perfect either. No model is perfect, I guess. But I want to perhaps try and link this back to what we see in simulations of these galaxies, where there have been some theoretical work to try and model the extragalactic RM distributions. So, and on the left from Basu et al. 2018, they simulated 10,000 disk galaxies with a range of inclination, azimuthal angles, and effect parameters. And on the right is COVAX plus 2024, where they used the TNG 50 simulations with 16,000 plus-ish galaxies and a range of rotations and FRB positions in each galaxy, because there they're focusing on FRB host galaxies. And then the host galaxy RM contributions are just calculated for each sightline. And in both cases, they found that the host galaxy RM distributions are well modeled by the combination of a Lorentzian and two Gaussians. A Lorentzian for the wings of the extragalactic RM distribution, but also a Gaussian for that's related to something like the product of the field strength and the electron density, and a second Gaussian to describe the peak at around 0. If you want more details, I invite you to look at the paper. And then I should also stress that these are rest frame values. The distribution I've been showing has not been corrected for either individual redshifts, or we have not done yet a statistical correction. And then just to put maybe a more schematic picture to it, here's me drawing the RM quantity in white arrows and multiple different sightlines. And in those studies, there is a redshift dependence, but they generally see that the azimuthal components of the magnetic field is much stronger, a few times stronger compared to the vertical and the radial components of the field. So an observer, us, would see contributions to the RM from the azimuthal component. And if we do get these high RM-ish RM values, we may be seeing these edge-on orientations, maybe. And so, motivated by that, I made the same Lorentzian plus 2 Gaussian fit to the base cat 1 and base cat 2, which is shown in the dashed lines. And the slightly more complex model fits the observed distribution slightly better, but actually not that much more. But I guess the main takeaway is that the Baseband model, at least requires some Lorentzian-like component to at least describe the wings of the observed extragalactic RM distribution a bit more reasonably. And this maybe tells us that some FRB sources tend to result in these galaxies, as I was trying to motivate before, similar to what Alexa Gordon showed us yesterday, and plenty of other work as well. And then some very recent work archived last week by Wovatsky et al. from last week, from the craft survey of about 35 FRBs, found a potential correlation between the extragalactic RM and also the ratio of the semi-minor to semi-major axis for the host galaxies, and maybe pointing to edge-on orientations. Now, what I'm offering here is an interpretation of what's going on, not the interpretation, or I'm not going to claim anything like that, since we don't have enriched information. But the talks yesterday, including by Alexa, was showing us that they're likely delayed channel host 2. So comparisons with other simulations of elliptical galaxies or other types of environments would be instructive in this case. Okay, now looking ahead, there's much more to do with the base cat 2 sample that we have. For example, with the baseband localizations that we have and we'll do, we'll look for host associations with the path framework. Something I didn't quite touch on because of time constraints are depolarization and variations in the polarization angle profiles, various things that Jiarui was just talking about in the last talk. But it's an extension of what in the base cat 1 sample, what Ayush Pandhi led for a couple months ago. We do want to do simple correlations with burst properties and many more as well. And of course, with the full CHIME outriggers array, it's just amazing how we have these precise host localizations now. And hopefully that means we'll get more redshifts, as we were discussing yesterday at the end of the day, so that we can more precisely constrain the magnetoionic environments around or near FRBs. So to conclude, we're now working with a sample of polarized non-repeating FRBs in base cat 2 with expansion of at least 10 times. But again, we're still working on the sample. And we do see FRBs that are generally highly linearly polarized. I think I didn't even mention that. Whoops. Anyway, but I showed the distribution of the extra galactic RM, and it seems to require some sort of Lorentzian to describe the wings of the distribution. And I argued that in comparison with these theoretical simulations, that might point towards disk-type galaxies, at least in those environments. And again, results of preliminary analysis are still ongoing, but since we are at FRB 2025, if you have any ideas about things to play with, things to look out for, papers to compare to, or whatever ideas might be going on, I'm more than happy to chat with you either here this week or by email. With that, I'll take questions. Thank you.
Right, any questions for Mason? Nice, great. Let's start down here.
A reminder to please introduce yourself.
Hey, thanks for the really interesting talk. I'm Pawan from Sunwan University. So I was just curious about the thing that you probably did not touch upon on the depolarization aspect. Do you find any significantly depolarized bursts in the CHIME band in your Basecat 2?
Yeah, I think Ayush is actually better positioned to answer that from Basecat 1 because we've not started on that yet. Because we plan on doing very simple looks, because the chime band is relatively narrow, between 400 to 800 megahertz. We'll just do a simple fraction between 400 to 600, 600, 800, but we have not done that yet, so I can't comment.
Thanks.
But thanks for the question.
Hi, Mason. Thanks for the talk. This is Marcus Lower from Swinburne University. I was wondering if you could say a little bit more about how the Basecat RM distribution compares with the ASCAP craft sample.
Oh, yeah, I guess from Wovalski et al. Yeah, I guess it was a slide from here. So yeah, I think when the paper came on the archive last week, I was very curious about what this looked like. But I guess with 35 FRBs, the distribution I've shown here in lime green, and the fit with the Lorentzian plus 2 Gaussian in light green as well, and the fit isn't so good. So I think there we can't say too much more other than we'll like definitely a bigger sample of polarized FRBs from all, including CHIME, but also with craft. But again, the interesting result with the host galaxies was like what I said before. That was very well noted.
Great, thank you.
Thanks. Sunil, can you unmute yourself, please?
Oh, yes. Thanks. Hi, this is Sunil from Northwestern Chicago. I was just trying to, well, this could be a question for clarification because I might have just misunderstood it. So in your RMEG versus DMEG plot, you don't see the negative correlation, which is just the indication, as you mentioned, that the RM is likely coming from the circumburst medium and not the interstellar medium of the host. But you also showed that the RM distribution of the bursts are Lorentzian, which could be explained by basically the ISM being a disk. So how do you reconcile these two? To me, it sounded like they were contradictory, but maybe I'm misunderstanding it.
Yeah, sorry, I only caught kind of a 75% of the question in the front here. If I understood the question, I think we would need host galaxy associations to really get a better sense of what might be going on in distinguishing between the different contributions, possibly. If I didn't quite catch your question, feel free to just message.
Yeah, I'll just put it on Slack. Thank you.
Okay, thanks, Sunil.
Okay, let's thank the speaker again.
We also just want to get rid of the subtitles.
I'll leave you to it.
Yeah. So I'm gonna try and be off. And it was Google Slides, right?
Yeah.
Amazing. And this is yeah, I'll grab that. You can use this if you want, or just the errors. Awesome. I'm not gonna put this on just yet, so we quickly introduce ourselves. But hi everyone, my name is Jakob Faber. I'm a third-year graduate student at Caltech, working with the DSA 110 collaboration, the Deep Synoptic Array 110.
And I'm Ayush Pandhi. I'm a final year PhD student in the CHIME FRB collaboration at the University of Toronto.
Right. Awesome. So today I'm going to be telling you about a sort of unique joint venture between these two collaborations that we're a part of, and the special, unique, very interesting things that we can do when we use them in tandem. So, or use the instruments that both collaborations use in tandem, namely the DSA 110, located in Southern California, and CHIME FRB, located up in British Columbia, Canada. So I won't belabor you with the back of these baseball cards. You've heard enough about these observatories already, but broadly speaking, CHIME FRB, amazing FRB detecting machine, wide field of view operating between 400 and 800 megahertz. The DSA 110 geared towards localizing FRBs to within arc-second precision and operating at L-band between 1.3 and 1.5 gigahertz. Now, the two observatories fortuitously share a substantial degree of overlapping sky coverage, which is not on purpose, but amazing for us because that allows us to do the science that we're talking about today, and possibly, and eventually, as you'll see now, simultaneously detect individual FRBs, actual individual bursts from the same source. This offers a unique opportunity to constrain propagation effects across a wide frequency range, 400 megahertz to all the way up to 1.5 gigahertz, which we'll be talking about today, but also their emission physics. So the sample. The sample is comprised of 16 FRBs in total, 12 of which were sufficiently bright to be stored or dumped as raw voltage data at both observatories. It comprised one repeater, which only repeated twice at the DSA 110, observed once at CHIME, and the rest non-repeaters. Now, the search itself was quite simple, performed simply by cross-matching the two detection catalogs, searching for coincidences in dispersion measure, times of arrival, obviously, as well as sky position. Now, to classify these as codetected FRBs was a little bit more challenging, but relied specifically on precisely measuring the time of arrival such that we could say whether or not it arrived within the expected light travel time between the two instruments, which depends both on sky position and the actual baseline. Now, what I mean by this is you can see on the map here, CHIME FRB up top, DSA 110 down below, fortuitously located at very similar longitudes. The CHIME telescope, being a transit telescope, stays fixed on the sky, whereas the DSA 110 is only steerable in elevation and typically operates in drift scan mode, parked at a certain deck, which over the course of the roughly 2 years that we looked at observations for, was positioned at a deck of roughly 71 degrees. Thus, we expect roughly the same time arrival offset to occur between the two observatories for all of these bursts, where it arrives at CHIME just a little bit earlier than it arrives at the DSA 110. Now, this TOA offset, roughly speaking, is plus or minus 0.1 milliseconds or so, is 2.5 milliseconds. And you can see that if we actually plot the primary beam of the DSA 110, which given the narrow field of view is roughly where we expect those FRBs to fall, this time of arrival offset shouldn't change very much. And as you'd have it, if we look at the bursts in our sample, all of them modulo some uncertainty based on their burst width and their DM variations that might lead to little variations in the TOA, all fall within this expected time of arrival offset, thus supporting our conclusion that these are indeed co-detections. They're the same bursts detected at both observatories. Now, what can we do with these? So much. It's really staggering, but time is limited, so I'll briefly talk to you about sort of what we see as far as the propagation effect in intensity, namely scattering, which manifests as two separate observable phenomena, mainly pulse broadening and scintillation, caused by some sort of scattering screen or interstellar plasma through which the wavefront propagates. Now, scintillation, the DSA 110 is perfectly geared toward this, whereas pulse broadening, that's really where the CHIME data shine. Now, what I mean specifically when I say scintillation and pulse broadening, scintillation is an interference phenomenon. So when the wave propagates through some sort of interstellar plasma, the path lengths will differ, imposing a phase change, and those will constructively or destructively interfere, leading to these striations in intensity that you see across the burst. On the left here, typically we measure this by taking the autocorrelation function of the time integrated frequency spectrum, looking for a characteristic scale that ought to evolve with frequency. Both of these phenomena are chromatic, and if occurring due to the same screen, are chromatic in a similar fashion, scaling by the same sort of power law index. Pulse broadening manifests as this delay in time, where we fit a pulse broadening function, typically an exponential, as opposed to the ACF, which we typically fit a Lorentzian, and we look for that characteristic smearing in time, basically due to the path length differences of the rays in the wavefront. Now, when we actually look at the scintillation, we often find in FRBs that it's imposed by the Milky Way. The same is true for 11 of the 12 bursts in the sample, all of which show scintillation bandwidths at frequency scale consistent with what we expect from the Milky Way. And because this bandwidth ought to narrow towards lower frequencies at CHIME, it becomes a little bit harder to observe, but we see that it actually scales consistently for 4 of the 12 bursts that we measure scintillation for in CHIME. Now, the last point I want to make is that what this sample is really geared towards is, or really sort of allows us to do at scale, is constrain two screen phenomena. So where you have one screen that's maybe a little bit closer to the host galaxy and one that's within the Milky Way. And these two screens are actually, we can constrain the presence of these two screens if these two, the broadening and the scintillation, don't necessarily agree or are Fourier inconsistent, meaning they don't adhere to this relation, or they do adhere to this relation, the inequality doesn't hold. This enables us to place a constraint on the distances of these screens collectively. These two are degenerate phenomena, but we can place an upper limit on the two. And we basically find that the two screens, when we basically find for all the bursts in the sample that they are indeed Fourier inconsistent, highlighting the presence of these two screens, which you can see on the right panel here. And I'll leave you with this. So this is basically the constraint that we get, the upper limit on this multiplication of the two, which when compared to previous two screen constraints is comparable. So all falling likely roughly within a virial radius, supporting the conclusion that scattering, the pulse broadening itself, is occurring within the host galaxy, whereas the scintillation is occurring within the Milky Way. This roughly doubles the number of events that we can constrain this for. So this is really a leg up in our ability to talk about the presence of these screens, and then ultimately moving forward later, constrain things, constrain the plasma turbulence properties, et cetera, within the local environment of that fast radio burst. And I'll hand it over to Ayush.
Great. Thank you, Jacob. So I will talk about the frequency-dependent polarization effects in the codetected samples in the second half. So the first effect that we're looking at is how does scattering affect the polarization angle or PA profiles of these FRBs. So here's a simulation where on the left, we have a simulated FRB and its PA swing. And then on the right is what you get when you scatter that FRB. So now in the leading edge, which is still coherent, you still get a bit of a PA swing. But in the scattering tail, where now you've scrambled the pulse phases, at any given time, they average out to 0. So you get this flattening in the PA profile in the scattering tail. Here's an example of what that looks like in our data. So here on the top panel is the DSA detection at 1.4 gigahertz, where in the inset you can see an 80-degree PA swing, versus in the CHIME detection at the bottom, now it's much wider due to the scattering, and the PA profile has flattened. And there's also a really good example of this in Mawson's talk tomorrow, so I recommend that you watch out for that. In our codetected FRBs, we only see this in 2 out of the 12 codetections, and in most of the FRBs, actually, they show constant PA profiles at both L-band and at 600 megahertz, regardless of whether or not they're scattered. Comparing this to most FRBs in literature, we know that most of them have constant PA profiles, but also that some FRBs, like this 121102 burst at high frequencies, we see constant PA profiles even though we don't see any scattering. So we know the underlying population does have some FRBs that do have intrinsic constant PAs, but also our result is highlighting this bias where you have a fraction of the population that did have an intrinsic PA swing, but now has been flattened due to scattering at lower frequencies. So we don't have a large enough sample to figure out exactly how many FRBs this happens to in the population, but it's highlighting that this bias does in fact exist. Next, we looked at the linear polarization fraction, or L over I, as a function of frequency, and we fit a few different models for how that could work. Here, it's just a constant model, so it remains the same at every frequency. Here is a beam depolarization model, which Rob explained really well in his talk on Monday. But the summary is when you travel through an inhomogeneous plasma, the light will scatter, experience slightly different Faraday rotations. And so when you sum up all of the light, you get depolarization from the interference in the PA angles that are different. In this final model, we've taken that beam depolarization and we've added an effect that we see in pulsar emission. So this is a birefringence effect that happens specifically in neutron star magnetospheres, where you get these X and O modes, these orthogonal wave modes, and they propagate at slightly different paths. At higher frequencies, they propagate closer together. And so the observer might see a superposition of them and they interfere and depolarize. While at lower frequencies, they are further apart, so you might only see one or the other. And they're independently highly linearly polarized. We fit these different models using an MCMC fitting routine. And here is an example where the best fit tells us that there's beam depolarization, so the presence of inhomogeneous plasma around the FRB. And here's an example where we see this birefringence effect, where at higher frequencies, you're starting at lower linear polarizations, increasing and then going back down due to beam depolarization. The asterisk here is that the birefringence part relies on us detecting the exact same component of the burst at both CHIME and DSA. And that's an asterisk because remember, we're missing data between the bottom of the DSA band and the top of the CHIME band, so we don't have continuous coverage to visually confirm this is in fact the same component. We just believe that it is based off of all of our tests that we've done. In terms of the best fit models, 4 out of 12 of them have constant linear polarization, 5 have beam depolarization, and 3 are best fit by this more complicated birefringence model. In terms of the literature, we see a few examples of depolarization only, and most of them are in these repeaters with extreme environments, and only a couple in non-repeaters, and we only have one real example of this repolarization behavior. What our results are telling us is that maybe these depolarizing environments are actually more common because we see them in more than half of our sample, but we only can characterize them because we have such broadband observations. And so it might be more common than we think to have these inhomogeneous plasma environments around FRBs. The second thing that we find is potential evidence for magnetospheric emission through this birefringence process in a few of our bursts, again with the caveat that it's assuming that we're detecting the exact same component between the two telescopes. So with that, we will leave up a summary slide and we can take questions.
Okay, any questions for Jakob or Ayush? Marcus?
Right, Marcus Lower from Sorbonne University. Very cool work. So you looked at linear polarization with frequency. What about circular polarization?
Yeah, so that one's a little bit more challenging. So DSA does a really good job calibrating their circular polarization, but CHIME, we don't calibrate it. And so we have about a 20% uncertainty in circular polarization. So we have looked at it, but it's hard to tell any specific like frequency dependent effects in circular. Yeah.
Cool.
That's really cool work. I'm Pawan from Sorbonne University. So I was just curious about the sense that you have in terms of what fraction of population would you actually see to be depolarized, given that you have a large bandwidth, which is ideal for such detections.
Yeah, so in our co-detection sample, out of the 12 co-detections, we saw evidence for beam depolarization in 7 of them. So it's, go back up. So it's the 5 that are best fit by the beam depolarization model, and then in 2 that are best fit by the birefringence and beam depolarization, we actually see evidence for like a downturn in the yellow bar.
So do you expect if you have even more large bandwidth, what do you have a sense of just from like simulations or something?
Yeah, it's hard to extrapolate from such a small sample, but it seems like it's at least more common than only the handful that we have in literature so far out of like the hundreds of polarized FRBs. So definitely more common than that. Yeah.
Thanks.
Question over here.
Hi, it's Matt Dobbs from McGill. One of the CHIME outriggers is co-located with the Allen Telescope Array, and their new upgrade is coming along pretty well. That would take us out to many gigahertz. They don't have much of a detection pipeline, but it would be easy. They have a good baseband buffer. So with that possibility in the future, how exciting would it be? And the overlap in sky, their beams are smaller, so it'd only be a few events, I guess. How exciting or not exciting would it be to explore that sort of?
I think potentially very, with a strong emphasis on potentially. I mean the one of the things that we haven't actually done is characterize why we only see the number of events that we've actually seen here. So if the two are well suited positionally or as far as sensitivity goes to actually detect the same events, amazing. Yeah, I mean the broader the frequency coverage, the better all of these constraints can be, and the more precise that we can be in discussing radio properties literally across the band. But I think if does the Allen telescope array localize well?
It should be able to, and they have a baseband buffer, so it's as good as the post analysis.
Yeah, then that's perfect, and that can again that's in addition to the DSA 110, which is already positioned just out. So yeah.
And I think one of the more interesting things is also that, we're going up to L-band here where we know there's a lot of FRBs, but going even higher than that, we don't know how many FRBs actually exist at higher frequencies, or we don't know it super well. So that would be just figuring out how many do actually exist in the co-detections compared to what you should have detected. I think would be a simple and really interesting answer.
Okay, that's all the time we have for questions. Let's thank the speakers again.
Yeah, yours is on this PowerPoint, right? Yeah. Second. If it's not currently up, I'll just smart. It's here. All right, get you back to start.
Yeah. Okay, just start.
Yep.
Yeah. Thank you.
Okay, next speaker is Wang.
Yeah.
Who will be telling us about depolarization.
It's the propagation.
Sorry,
I'll share. Okay.
We shared that on Zoom. Sorry about that.
Okay. Thanks. Okay.
Oh, okay.
Maybe just start.
Yeah. Maybe I'll just explicitly share your PowerPoint. That might work better. And yeah, make sure that stays plugged in. So it should be sharing. How does it look on Zoom? The presenter mode.
Presents.
It's annoying. It wasn't doing it before. Dude.
It like creates a new screen. So if you share first and then sorry, if you full screen this first.
Full screen it, then share.
And
Okay.
then share. Right.
Okay.
Yeah.
Then share this one.
Yeah.
What about now?
Does that look good? Right.
Okay.
Go for it.
Thank you. Good morning, everyone. I'm Wang from University of CES. So today I will share my recent work about the propagation-induced polarization properties for fast-radio burst. So I will introduce from these 4 parts. I think Jiarui have given very nice review for the polarization properties for fast-radio burst. So I just share some very intriguing parts here, which is the frequency-dependent polarization properties for the fast-radio burst. So you can see that from this pictures, you can see that not only the U and Q are oscillated with a frequency or wavelengths, the circular polarization components, we can also oscillate with the frequencies. This phenomenon has also been found with some burst from some sources, and also have been seen from some magnetars and pulsars. So according to the plasma physics, so this phenomenon may be caused by some propagation effects like conversion. So based on the plasma physics, so if the magnetic field is strictly perpendicular to the line of sight, so there will be some Faraday conversion happens. So in that case, the basic modes, the O modes and the E modes are strictly, they are 100% linearly polarized. And but these two modes with a different frequency, with different arriving time, different phase velocity. So the submission wave of this, so the submission wave can generate some circular polarization components at some frequencies. That is so-called Faraday conversion. So it actually converted it actually let the linear polarization components converted into circular polarization components. But in reality, the truly astrophysical magnetic fields could not be strictly perpendicular to the line of sight. So if the Faraday conversion happened, there must be Faraday rotation. The question is how to measure them, how to know that how to know the contribution from the Faraday conversion and the Faraday conversion and Faraday rotation individually. So that is the biggest question. So someone proposed some methods to solve this problem, like the generalized Faraday rotation. So if we treat the Faraday conversion like a generalized Faraday rotation, in other words, we can assume that the polarization vector is a generalized power law relationship, and then we can introduce some rotation metrics, and then we can use this method to feed the trajectory of the Stokes parameters in Poincare sphere, and then we can get so many parameters like the alpha, which is the power law index, and there's so many angles. But this method only give you some parameters. You could not find the physical properties directly from these parameters. So in order to solve this problem, we propose another method which is based on the analytic solution of the transformation function. So before that, in general we assume that the FRB wave can go through the magnetic plasma medium. But even we don't know where is this plasma medium, we can just assume that there is a foreground and a background rotation measure layer here. Before we solve this equation, we need to select coordinates in which we select the coordinate which is the intrinsic plasma coordinate, because the subscripts of the Stokes parameters of U can be ignored. And the FRB waves always have a strong, extremely bright temperature. So the emissivity from the medium itself can be ignored. So this equation can be mostly simplified. But another question is actually the v-axis could not be always parallel to the north axis of the Earth. So we need to change this equation, change the solution back to the observer's lab frame. So and then after this operations, we can get the solution. I think everybody dislikes the equations, so I will skip this part quickly. Back to the and now we discuss the two two cases of the plasma medium. One is the cold plasma, and the other is the hot plasma. Cold plasma means the non-relativistic, hot plasma for the ultra-relativistic. So in the cold plasma cases, we can find that if the number density is really large, the free absorption will dominate the propagation. But for the lower density, and for the lower magnetic fields, the Faraday rotation can dominate the propagation. And for the higher magnetic fields, the Faraday conversion can dominate. The cases is different, really different for the hot plasma cases, in which the Faraday rotation is decreases with the Lorentz factor increasing, but the Faraday conversion rates can get larger. So this is the most differences. Therefore we can find that for a hot plasma medium, the Faraday conversion can be much easier to occur at a higher Lorentz factor. And we consider that a very intriguing scenario, which is called the mixing Faraday spectrum. The mixing Faraday spectrum have a comparable Faraday rotation and Faraday conversion. So in that case, we made some simulations with different incoming wave properties, like showing in these pictures. We can we can also find that there are some common properties, like there is some precision in Poincare sphere with the frequencies, and we can find that both the Q, all of the Q, U, and Weiyang parameters can oscillate with the frequency or with different phases, and then we can also find that the position angle looks like an S shape. So the trajectory in the Poincare sphere in that case is very similar with the Fulcon pendulum. The Fulcon pendulum actually it consists with the two different frequency different rotations with different frequencies and different directions. One is the Earth's spin, the other is the pendulum itself. So that is similar with the mixing Faraday spectrum. One is the Faraday conversion, the other is the Faraday rotation. Actually, both the cold and hot plasma cases can generate such scenario. So the cold plasma requires a large perpendicular magnetic field components, but for the hot plasma, it does not need. But the hot plasma just need a large Rother factor, and the hot plasma cases will always predict a large dispersion measure here. We then develop this analytical solution method to develop the code to help observers to make some data precision. That's my students Xiaohui Liu helped me do this. We have Faraday rotation, Faraday conversion, FRB here. So all of these words have the same initial alphabet, which is F. So we call this method mixf. So the mixf code has been published in GitHub. If you like, if you want to use this method to make some data precision, you can find it. So by comparing with the generalized Faraday rotation methods and the mixf methods, we can find that both of these methods can feed the data very well. But the mixf methods can show can give you the more physical information of the plasma medium, like the magnetic fields, column density, and also for some incoming wave parameters. And we also use this method to feed the observation data for another repeating FRBs. And back to the question: what is the plasma medium here? So some FRBs are associated with a persistent radial source. So if we assume that the FRB wave can go through the plasma medium or directly go through the persistent radial source, so I can see that by considering the synchronous radiation mechanism, the persistent radial source is a hot plasma here. Ultra-rare is hot plasma, so it can generate synchronous radiation. That is the very wonderful candidate for the persistent radial source. So we can see, but based on this equation, we can find that it is very easy to generate Faraday conversion here. But the question is the observed number density or of the event rates of the Faraday conversion is inconsistent with what we predict. So basically, I don't think the persistent radial source may be the modeled hot plasma medium here. So in order to generate Faraday conversion and for some repeating FRB source, it might be cold plasma medium here. Maybe possibly some stellar wind from the companion stars or something others. So the last part I really want to show you is the results from the recently very active repeater. So in this source, I actually have detected so many polarization samples, and among these samples, we have detected so many bursts with the Faraday conversion here. We can find that the Faraday conversion can occur within several days, which indicates that it looks like the perpendicular magnetic field appears within several days. And we also find that the rotation measure contributed by the background field is roughly equals to 0. So which means that the plasma medium is really close to the FRB source itself. So it looks like a binary system. Just assumption. So for the summary parts, the most important thing is we propose a new method to process data, which is called the mixf method. So if you do some data precision of the polarization data, if you like, you can use our methods to make some data precision. It may help you. And one notion here is if you find that the circular polarization components is frequency dependent, like showing some oscillation structures, you will not only use the focus parameters of U and Q to derive the rotation measure. That is wrong, because you should consider the Faraday conversion here. And the last part is we can use these methods to study the magnetic elements for fast burst. It can help us to understand the truly physical parameters of the plasma medium. So that's what I really want to share with you. Thanks.
Hey, it's great that you were under time, so we've actually time for questions.
We'll go at the back here.
Hi, Weiyang. I am
Hi.
Om Gupta from UT Austin. I have a couple of questions. One is, what are the initial Stokes parameters that you have input into your model so that you can fit the GFR spectra? And my second question is,
yeah, maybe it's too small. I guess you can see the input parameters include magnetic fields, the angle between the line of sight and the magnetic fields, and the Coulomb density here, and the temperature of the medium, and also the last three parameters are based on some polarization properties from the incoming wave. So we need we need 6 or 7 parameters here.
so so you need some non-linear, like the initial wave should be completely linearly polarized, or you need some additional polarization going in to your medium.
Yeah, the fitting result shows that then for some bursts the incoming wave is not totally totally linearly polarized. So actually the incoming wave may have some circular polarization components.
Okay. And my second question is, I did not understand. You said the PRS should be capable of generating the circular polarization because of the hot component, but it's not matching the RM, the predicted RM that you want. Is that right?
Sorry, what?
If I'm not sure whether I understood, you said that the PRS should be capable of generating the required circular polarization from Faraday conversion.
Yeah, for the highly circular polarized wave, it might be but possibly dominated by not dominated. It may cause both from the propagation effects and the intrinsic mechanism. For the propagation effects, you may find that the circular polarization components is frequency dependent. But from Jinchen Jiang's paper, we do not find we did not find such observation. So it's possibly dominated by the intrinsic mechanism. But the propagation effects like the Faraday conversion can also generate some circular polarization components here.
Okay, thank you.
Thank you for the talk. So do you see any evidence, I guess, in fitting these repeating bursts, do you see any evidence of multiple Faraday rotating media, for example, a hot and a cold plasma, or some superposition of whether you have like a local rotating medium and then and then a ISM rotating medium, or is it largely dominated by a single Faraday rotating medium?
Actually, we don't, because I think the question is actually we don't know where is the plasma medium here, possibly located at the host galaxy or in our Milky Way. So it depends on because there is some degeneracy between the background rotation measure layer and also for the foreground rotation measure layer here. So possibly we can know, possibly one day we may know where is the plasma medium here by determining by determining the value of the rotation measure contributed by the foreground layer here, I guess.
Thank you.
I think that's all the time we have for questions, unfortunately. So let's thank Weiyang again.
Yours was PowerPoint again, or?
No, I said I'm gonna touch it. You're free.
Oh yeah, just what was the format?
Keynote.
Ah, right. Oh, and I think I need to, yeah, I think I need to reshare the.
Oh.
Good.
Okay, our next speaker is Ilya Khrykin.
Thank you. And first of all, let me thank members of F2D4 collaboration for their help with this project, and specifically Alexandra and Luis. So Alexandra gave a very interesting talk yesterday. Luis will be speaking tomorrow, I believe, and I urge you to go and check out their amazing work. And I think that I should probably start with addressing the fish in the room. Some of you might be wondering, why did I put a very surprised fish in my slide? So as astronomers, I think we all know that when you start a new project, you build a new telescope or start a survey, the right name gives you at least 50% of success. So internally in F4 collaboration, this project is known as Mahi Mahi. Hence I asked ChatGPT to generate fish in the galactic magnetic field. Speaking of, what do we actually know, or what we think we know about the galactic magnetic field? So we know, or we think we know, that there was a primordial magnetic field in the beginning of the universe. And then the later stages, after the structures grew, galaxies formed and evolved, the magnetic field got amplified, and probably all galaxies right now should have magnetic field. And this is a nice example from the hydrodynamical simulation that shows a snapshot on one random halo and the distribution of magnetic field of different strength in and out of this galaxy. So it's fairly easy to simulate magnetic field in simulations, but it might not be that trivial to detect them in real life with observations. And FRBs are actually very uniquely suited as probes of magnetic field, as we heard all morning today and yesterday as well. And noticeably, well, you all remember this paper by X. I think it was the first paper that actually probed the magnetic field in the foreground galaxy of the FRB. Unfortunately, it was just one galaxy, one FRB, so statistic is not really great. And you know, after all these years, it's interesting if we can do better, because maybe we have more statistical information. So I'm not gonna go into the details what RM is. You heard about it today all morning. We also heard a very nice talk on Monday about all the propagation effects, but I want to stop for a minute on what environments can actually contribute to the observed radiation measure, because I think it's important. So we know that, you know, FRB originated in the host galaxy, and the first environment that might and probably contributes to the observed radiation measure is the radiation measure associated with the host ISM or FRB progenitor itself, which is given by this term RM local host. Then the signal travels further, it goes through the halo of the host, which might also contribute to the observed radiation measure. Finally, it goes through the IGM and might intersect the halos of the foreground galaxies. And then it reaches us in the Milky Way, giving us the final contribution. So usually people ignore these two terms. And well, I guess mostly because there is no information about the foreground structures, or is there? So one of the motivations for this work is actually check if can we simply ignore these factors. Yeah, one assumption that I will use as others is that IGM contributes 0, which is warranted given that the estimates show that this radiation measure at least 2 or 3 orders of magnitude smaller than what you would expect from the galactic environments. So we have assembled a sample of 14 FRB sightlines, and besides of course, the requirement of very nice, good localization. We also require these FRBs to have measured rotation measure. Sorry. And also, we need spectroscopic samples of the foreground galaxies. So it's just a sample summarizing the observables. Better you can see this from these plots. On the left side, you see the extragalactic rotation measure plotted as a function of redshift. So our sample is black, and then I'll show two other samples from previous works. And on the right side, we plot rotation measure, well, extragalactic rotation measure is a function of the direct measurement of the dispersion measure in the host of some of the galaxies for which we had Muse data. These measurements come from the very nice paper by Lucas Bernales-Cortés, to which I really want to refer you. It's a very interesting way to measure the DM of the host directly without invoking the McCart relation. It's probably the future of the field. Anyway, so this is the observables, right? This is one requirement of observed rotation measure. What about the foregrounds? So luckily, we have FLIM-FLAM, which is a survey aims at mapping the foreground structures of multiple FRB sightlines. And last year, we published the first data release and the first analysis that gave the first measurement of the distribution of cosmic baryons. And along with this measurement, we acquired lots of information about foreground structures, specifically halos of galaxies and clusters and groups. So this plot summarizes what we have in our sample for the foreground halos. Not all sightlines are covered by FLIM-FLAM data. We also used Muse data for those that lack FLIM-FLAM data. And basically, I mean, it might be a busy plot, but the message from this plot is that each sightline intersects at least one halo, when in reality, probably more than that. So it's interesting to check if they actually contribute to the rotation measure. And this is time to start building our model for the observed rotation measure, which is given for a single FRB by this equation. And let's go quickly each term at a time. So first we start with the Milky Way contribution. We, of course, have the Faraday rotation maps for our galaxy. And for given a position of the FRB on the sky, we can get nice, well, kind of Gaussian distribution for the rotation measure of the Milky Way. Next, to describe the rotation measure of each individual foreground halo, we use the modified NFW profile, which is characterized by mainly two parameters, which is mass of the halo, M halo, and F gas, which is the average fraction of cosmic baryons that reside in ionized CGM of individual halo. If you integrate this density profile, you can get the rotation measure of a given foreground halo, which depends on this B parameter, which is the average magnetic field in the foreground halos. So if you do this, one important thing is that halo mass is a very uncertain thing, and we should take this into account. And we do by randomly sampling the Gaussian distribution of the halo mass for a given halo. And so if you do this, you will actually get not one RM measurement for halo, but a distribution which would look like this. You can notice that it's only has positive side, just by construction, which corresponds to the case where the magnetic field is aligned with the sight line and directed towards the observer. In order to take into account the other case where the magnetic field is directed in the opposite direction, we simply mirror this distribution to the negative side, and then we have this full distribution rotation measure for given foreground halo. Then we move to the halos of the hosts. We use the same modified NFW profile to model it. Again, we take into account both geometrical options for the magnetic field and distribution. Well, this is an example distribution that looks like this. And it depends on this B parameter, which is the average magnetic in the halos of the hosts of the FRBs. Finally, we come to the RM of the local environment. Again, luckily from FLIM-FLAM, we have direct measurement of this dispersion measure in the local environment due to the ISM or FRB progenitor. And using the conversion between DM and RM, we can directly sample this distribution, this posterior distribution from the FLIM-FLAM DR1 results, and get the RM local distribution that I've shown here. Again, the geometrical factors are taken into account. So we have 4 parameters, 3 magnetic fields in different environments and F gas as well. And in order to infer them, we use MCMC. And the first step is, of course, to build the likelihood function. I'll quickly go through the steps of doing so. Well, of course, you create the parameter space. And for a given point in this parameter space, you find the corresponding distributions of rotation measures in the foreground halos, in the host halos, and in the local environment. You, of course, you find the RM distribution of the Milky Way, you sample them, combine all these measurements into one RM model, which is shown by this black histogram. And then you feed this histogram with the kernel density estimator and evaluate this KD PDF at the value of the observed rotation measure for a given FRB. So this is done for a single sightline. So you repeat the same steps for each point on your parameter grid, and then you compute your joint likelihood by summing up the log likelihoods for each FRB in your sample. Then we have priors that are listed here, and one important thing is that we require that the magnetic field in the halos will be smaller than in the local environment, which I think is warranted given the results of hydrodynamical simulations. One extra prior that we have is the prior on the diffuse baryon fraction, which is similar to what we used in flim-flam DR1, although there we didn't know the FIGM. Here we have a measurement from flim-flam, and we use for the means, which is shown here by the black curve, we use the average value from the flim-flam of 0.6. So when we sample this likelihood with MCMC, we get these results. So the top left is the F gas fraction, and then diagonally you have 3 different components of the magnetic field. One note, so we have a very nice measurement, looks like, except maybe for the foreground galaxies, because the posterior is still, well, it's not attached from 0. You cannot really distinguish the 0 case. That's why we put the upper limit instead of a measurement. Anyway, we can compare it with previous results. So I devised so the plot shows different measurements of the magnetic field in the CGM and the ISM of the galaxies. So on the left side, most of these measurements come from magnesium-2 observers in the quasar spectra, except Axis work and Kovac et al. They use lensing. On the right side, we have 2 works on the analyzing FRB samples. But I stress that both of these works assume that all rotation measures coming from the ISM of the host galaxies. So technically, in this right panel right now, there is no host halo contribution. We put our results on this plot, so you can see that. So our CGM measurements are consistent with others, and I think the takeaway message from the left panel is that halos are important. The degree of their importance is still to be determined, but I think that we should really have knowledge about the foreground structures if we want to correctly describe either rotation or dispersion measures. And on the right side, you see that we're in a good agreement actually with the average values for the ISM measurements, but the scatter is probably, scatter is given by the individual measurements, and plus some of this can be attributed to the halo contribution, which was omitted in previous works. So my conclusions here, we used the sample of 14 FRBs to measure magnetic fields in different galactic environments. For the first time, we split and measured the magnetic fields in host halos and ISM. We also put a limit on the magnetic field in foreground halos, and we estimated the fraction of cosmic baryons. So I think this shows the importance of the foreground surveys, and the future generation of telescopes will give us information, maybe if it exists, about the redshift evolution of the magnetic fields as well. Thank you.
For a couple questions.
Over to Stella.
Nice talk. Sorry if I missed this, but we saw a couple of examples yesterday of FRBs that had extreme RMs and then evidence of, magnetic fields local to the source that, are 10 to 100 times larger than, the maximum value in your prior. So are all of your sources relatively low RM? Are you explicitly excluding cases where there might be an extreme local contribution?
Yeah, so our sample doesn't have these extreme RMs. That's true. I think that they will significantly bias our results in the sense that probably that extreme RMs as well, as we heard yesterday or today, they are associated with some local screens, right, that give us these huge values. I don't think that our analysis is, well, at least not yet sensitive to this particular screen. So maybe in the future we will include them.
Thank you. I think it's fascinating what you're doing, but I think I might be missing something basic, and maybe you could just explain it in very simple terms. But what observational information, apart from model assumptions with NFW profiles, what is that? What observational information are you using to split to separate the B field components from one halo versus another halo? I'm not understanding that.
So well, first of all, we need to identify if there are any foreground galaxies between us and the FRB, right? So for that, we do the spectroscopy of the fields around the FRB position. So we determine the redshifts of the galaxies. If they're between us, okay, that's step one. Step two, we determine the impact factors of this, that these foreground galaxies have with respect to the sightline. Because when we construct the model of the halo, we need to determine if it's actually intersects the sightline, right? So we need to know how far away it is. And also we use then the photometric surveys to get magnitudes, which we can then convert to the stellar masses to the halo masses, in order to get the profile of the density of these halos. So these are the main observables that we use. So redshifts, photometry, and impact parameters.
Okay. So I don't understand where the field comes from. So the density, I totally understand. It's the field I'm not sure about, but perhaps we should talk at coffee
Sure.
Because this could be longer.
And I believe the next speaker is online. So if you're there, will you share your screen? Right. Oh, it's a video. Okay. Oh, apologies. Yeah, I'll start that. And we should be able to hear it, but just give a thumbs up on Zoom if you can hear this once it starts.
Okay, good morning, everyone. My presentation focuses on fast polarimetric observations of this hyperactive FRB 2024-0114A. These are my collaborators. Our data processing covers births from January 20th to August 30th in 2024. We analyzed over 5,000 bursts with SNR exceeding 20. And the complete catalog is in Junshuo's talk. He will give a detailed introduction later. This plot shows the overall analyzed results, including the temporal evolution of RM and the linear or circular polarization degrees. The mean RM of this value is around 363. And from the plot, we can see there is a very significant RM variations. So we think maybe there is a periodicity. So after removing a second order polynomial trend, we do the Lobscargo period search on the daily average RM values. And the result revealed around 60-day periodicity with 4.5 sigma confidence. Fast observation of this source is still ongoing, and we will check these results using new data later. Additionally, over 1,700 bursts exhibit circular polarization degrees exceeding 10%. And the circular polarization fraction and the absolute RM values of this source generally follow the empirical relationship proposed by Zhang Yongkun, matching a power law trend. And with the large circularly polarized sample, we identified multiple bursts showing Faraday conversion phenomena. Faraday conversion is on the electromagnetic field, electromagnetic waves transfer between linear and circular polarization states. If it occurs on Poincare sphere, is manifest as polarization vector deviating from the v-axis, and spectrally we can see the oscillations in Stokes V parameter versus the square of the wavelengths. And totally we detected over 200 bursts with these interesting effects. And so to further analyze these special bursts, we applied Weiyang's model to perform a parameter fitting. He has given a detailed introduction of this model just now. Maybe. And we think compared with the GFC geometry methods, this model can improve more scientific values for analyze. So we choose this model. And this is the result. The contour the parameter distributions. With these results, we obtain the constraints of the magnetic field and the electron density of the Faraday conversion medium. Well, Faraday conversion is the probe of magnetic ionic environment of FRB. We can learn about the knowledge of the magnetic field configuration through Faraday conversion. So it's very important to study the long-term change of this effect. But the most intriguing finding is that most Faraday conversion events clustered dramatically within a few days, especially for March 12th, with over 170 events. It's appearing just like flares. So we use the term Faraday conversion flare. And we think this may indicate a rapid magnetic field reconfiguration within the Faraday conversion media. And the further analysis is still ongoing. We are trying to find if there is still potential Faraday conversion events that we ignored before. And finally, this is a summary of my presentation. Okay, thank you.
We're going over time, so we're going to go straight into our last speaker.
Yeah, which is also pre-recorded.
Oh. But if folks have any questions, I encourage them to post some questions on the slide.
Here, what's that?
Hello everyone, I'm Wanjin from NOC, and sorry to pre-record this flash talk to prevent any network issues. I'm going to share our progress on constraining the physical scale of FRB local environments. And this work is supervised by Professor Dongzi Li, who joined the Tsinghua University, China, very recently. As we all know, repeating FRBs could show significant evolution according to many long-term monitoring campaigns. For example, the variation and even the reversal of Faraday rotation measure of some repeaters imply that they are surrounded by evolving magnetoactive medium. And because of that, current environmental models collapse into two scenarios: young supernova remnants and binaries. One of the key differences between these two models is their physical scale. So in both systems, FRB emitted by the celestial object may propagate through the foreground plasma screen in the closing environment, for example, the outer shell in supernova remnant or stellar wind in binary, and be received by the observers. The propagation path of FRBs could be different if the FRB source has a transverse velocity perpendicular to the sideline and the slide shows. Assuming that the propagation effects, including depolarization, scattering, and the RM variation, are dominated by the foreground plasma screen, we derive this formula to constrain the physical scale of FRB environments. Here is the main plot I want to show you. The variation timescales were obtained from the autocorrelation of the FRB RM variation curve for artificial inspection. For two FRBs that show significant RM reversal, the RM variation was split into different time spans to figure out the changing rate. The depolarization and the scattering scales are measured roughly at the same time with the RM variation. And furthermore, the error bars are not the measure uncertainties of the physical scale, but the range of velocity from 10 to 1,000 kilometers per second. The gray dashed lines refer to the spatial distance of this transverse motion. For comparison, we plotted the ratio between the spatial moving distance and the physical scale in the lower panel, altogether with the varying velocities. So we draw the possible parameter spaces of SNR and binary based on the galactic observations. And the plot is shown the physical scales of FRB 2020 1124A and 2019 0520B favor the binary model, and others lean to SNR, which is also distinguishable in the lower subplot. The ratio basically means the ellipticity of the binary orbit, or if there will be one, and the proportion of the central compact object is negligible with respect to the expanding outer shell, especially for the newborn supernova. And I will introduce some of the repeating FRBs to show the detail. And FRB 2019 0520B was reported to show a RM reversal in 2 years, observed by several telescopes. And so does FRB 2020 1124A. As for FRBs that show either secular RM variation or fluctuation, as indicated in the purple circles, they are more likely to be deeply modulated by the local SNR-like environment. Here, we investigated multiple FRB sources, including the R3. To conclude, this work is an independent constraint on the physical scales of FRB local environments without any prior. For example, the RM reversal is expected during the periostrum passage in binary systems. But we didn't use that knowledge, we just combined multiple propagation effects, including the dipole, the scattering, and the RM variation. So the result indicates that there are potentially different populations despite of the environmental model prior. I will end here. And any questions are welcome in the Slack, during the Slack and the email. Thank you all.
Right, that concludes this session. We'll now break for coffee. Let's thank the speakers again.